All right, thanks for the introduction. Thanks everybody for joining. I'm really excited about this one and looking forward to stepping you through this deep learning model we're building for mapping landslides. I want to start with just kind of stepping into the data landscape and setting the stage for where we are here in 2025. Brief intro to kind of what is computer vision and what are we doing with it? How are we using it? And then we're going to look at some results and kind of talk about where we're going. Really exciting time to be doing this type of work. So I want to acknowledge the team is way bigger than just myself. Aaron, Alex, Luke, Kaio on the BGC and Cambio side, leading the technical development with me, and also working with some collaborators from the University of Kentucky and Kentucky Geological Survey who really did a lot of. I hope they didn't get carpal tunnel. They certainly wore out some mouse batteries, digitizing landslides with us. So to get us kind of set up here in 2025, it's a really great time, right? We have all this data. We've got wonderful data sets all over the place. From a landslide practitioner standpoint, I'm mostly thinking about LiDAR. So the GIF on the left is just kind of showing in the United States the coverage of LiDAR over the last 20 years. And of course, many of these areas are starting to move into their second, third, or even more acquisitions of the same region. And again, when we're thinking about understanding landslides, then it becomes very obvious that we can start to do things like this example from Eastern Kentucky, where we can take a hillshade and look at it in 2017, do the same in 2023, and we can very satisfyingly identify landslides. So we're well on our way to creating a landslide inventory that has some time component to it. I think we can do a little bit better by integrating some quantitative change across the landscape. And so what I'm showing here on this exact same GIF is looking at LiDAR change detection, where the blues represent erosion and the reds or oranges represent deposition. There's a little bit of noise on the hill slope, but really now what we're looking for are these nice erosion deposition couplets. And so our eyes are really being drawn to the phenomenon we're trying to study. So we're kind of taking this idea of just cycling hillshades and we're bringing it up a little bit in terms of efficiency. This works because in most cases, most of the landscape does not change. So we decided to take this and just go for it. We went big. We went across this big area, 500 square kilometers in Eastern Kentucky, just a small part of what was impacted by a much larger storm back in 2022. And we just got digitizing. Myself and three others from the University of Kentucky, under support from the U.S. Geological Survey, we mapped about 6,500 landslides over this area, something around 200 hours. This was great. I did this over breakfast, just enjoyed mapping landslides before anybody else woke up. It was a good time. And just as a real brief aside, the real simple takeaway from this work, we're in the process of publishing it, but what we're unearthing is that, these convective storms in the eastern part of the United States can trigger as many landslides as hurricanes, which is kind of a big deal. We didn't really know that until we put all these polygons on the map. And so now we'll step into the computer vision part. Everything I've stepped you through so far, we talked about LiDAR, multiple epochs of LiDAR. We talked about looking for these patterns on the landscape where things change. So really what I'm talking about is this concept around pattern recognition. And we know that humans are good at it. We do it all the time. But what I wanted to set out to answer is, can computers do this a little bit better and faster than us? And so, of course, I turn to some of these more modern computer vision models that are coming out, or segmentation models perhaps, that are trained mostly, I always joke, they're on images of cats, but really it's just any images that are on the web. That's what a lot of these models are trained on. And effectively, there are some red, green, and blue images, right? An RGB image. And if you were to ask the computer, to draw a boundary around these cats, and you click on these two cats, it's going to do a great job. We know this for all sorts of objects. This works really well. Unfortunately, people are not out there feeding beautiful images of terrain data with LiDAR change detection into these models enough to where these models don't know what to do with this sort of image. It's not really tuned for it. And so we knew that we had some work to do to kind of revamp some of these architectures and try them out. And sure enough, when we play the same game to click on these two landslides, we actually can find them. And so these are the first time you're kind of seeing some real results from the model. And this is kind of what we're seeking out. Can we now do this at scale? How do we do it in a big data style approach? And so we don't have these RGB images. I'm not just going to create these hill shades with LiDAR change detection. We can do a little bit better than that by creating what I call a raster stack. And so this is effectively, we're taking any number of geospatial variables, anything you might put into a GIS or on a web map, and we're stacking them up here, lining them up by latitude and longitude over our AOI. And to start with, we kept it really simple. We just started with 2 layers, LiDAR change detection and slope. And we combined that with the inventory I mentioned earlier of these roughly 6,500 manually mapped landslides. And that's what we started with. And we're going to get more complicated. I'll explain some of that later. But we're just starting as simple as possible here. And so these are those 3 layers. The slope data forms the background, the terrain data here shown on the background. The LiDAR change detection is shown by the red to blue color scale, and then these yellow polygons are landslides. What you might notice is some of these landslides are quite large. Some of them are really small. There's probably some on here you can't even see. So we have this multi-scale problem. We need something that can identify big landslides, small landslides, and for that, we landed on DeepLab v3. This is a totally open model architecture published by Google several years ago. And that's where we are right now. And we're also exploring some other architectures. The cool part about DeepLab v3, I'm not going to go through this all. What I want to focus on is the cool part for us is this kind of multiple scales that it's well tuned for. So we basically show the model multiple neighborhoods of data. Maybe, we might show it 9 pixels over a 13 by 13 area, and then over a larger area and a larger area. And this lets us, again, look for large and small landslides, but it also helps us see the different parts of a landslide. So we might be able to have a really good picture of the toe and the head. Maybe the toe and the head are a little obscured and we can only see the laterals. So we really just want to have that multiple levels of context, just like you and me when we look at a map trying to find landslides. So once we train the model, we really don't need that much to run it. We just need the digital elevation model. We need a LiDAR change detection raster. And then we can go just from those 2 things. We can combine, in this case, again, I'm just very simply using slope as my only derivative of the DEM. And I'm mathematically combining it with the LiDAR change detection data, applying those model weights, and coming out with this probability mask. So let's dive into some of the results. What you're seeing on the left here, I'll just do a little bit of setup on some of these figures. On the left, there's a probability scale from 0 to 1. The purples are very low probability. The ones are very high probability. The polygons, the green, are the manually mapped landslides, and the yellow are the model predictions. And so the first thing that I notice on this is the predictions are quite hard, meaning the model is either really confident that a location does not have a landslide or that it does. There's very little in between. And so on the right-hand side, we can compare that with a more traditional kind of just LiDAR change detection draped on top of topography. And we can start to learn things about how the model's doing. So in some cases, like right here, the model's looking pretty good. In other cases, the model's identifying landslides that we missed, which is a common theme that really makes me excited. There's also things like missing a toe, false positives, right? So we can start to learn things. I'm going to go through a bunch more results here, but because of how hard these predictions are, which is something we're working on right now, but I think it's a little bit more intuitive just to focus on these simpler images. Just again, showing the model pick as the yellow, the manual pick as the green, and then the LiDAR change detection data. And so sometimes the differences are very subtle. If you look at both of these images here and all 5 of these identified landslides, if you gave me the model predictions or the manual mapping, in both cases, I'd probably vigorously nod and agree, right? I don't think there's huge differences. In some cases, the model does better. So on the left here, we have a nice, a tighter prediction shown by the yellow polygon against this landslide versus the green. And if you've ever done a lot of landslide mapping, you know how tempting it can be just a straight line across large areas and not really follow the signature of the landslide. I've seen some landslides mapped as pentagons, for example. So we know that because the computer's not dealing with a Friday afternoon before an exciting weekend, it's going to take the time to really tightly map these features if it can. The other thing is just identifying these pure oversights. So these 5 blue arrows point to landslides that we just missed in our mapping. And I know that, we just missed them, right? And a really interesting part of this is we're penalizing the model right now because it is arguing with us. It's saying, no, there is a landslide here. I sure see it, but we didn't map it. So that's our bad. So we need to work on that. There's also some domain expertise, right? A human mapper is going to intuit that this landslide certainly crossed the road. The model doesn't realize that, so it cuts it short. Other examples of deeper seated or lower magnitude landslides, like shown here, that the model misses. So a lot of things to really work on. But then we had to think about how do we look at this at the population scale, as opposed to just a few examples. And to set that up, what's important for us is really the false negatives. That's really what we want to avoid. We don't want to say there's no moving landslide here. So we want to have a really high rate of detections of landslides and really minimize these false negatives. And so one way that we've come up to do that is this kind of optimization curve where we look at the overlap of the model versus the manual polygons and the detection rate. So for example, if we only need 1 pixel to overlap before we call something a detection, we're going to hit about 90% of the landslides. And the 10% that we miss, they're really small. Like we're talking a few hundred square meters or less, which is cool. Like that's exciting from my perspective. If we go all the way out to the right here, just to help illustrate how this curve, works, we have 80% overlap between the model and the manual polygons at about 6 out of 10 landslides. And so a perfect model would look something like this. And so we're working on pushing this curve up and to the right. And that's exactly kind of where I'll close out here is kind of what's coming up next. We have a lot of tuning to do. We've got a lot of knobs to turn in terms of the model hyperparameters, the architecture, loss functions. It's really quite a bit of things we can try here to push that curve up and to the right. And then, of course, the other thing to not overlook is, again, remember, all we showed the model is slope data and LiDAR change detection. So we have a lot more to go. We have a lot more DEM derivatives that we're already computing, and we're going to be running some experiments to see what works well and what doesn't. And then, of course, we're also kicking off some pilot projects across North America that'll do a really great job toward getting us even more training data and seeing more landslides. So really excited to see where we can take this. I think this has been a super fun project, and I think it's a solvable problem. I hope I've convinced you of that already, and we'll see where we get in the next several months. So with that, I'd probably have a couple minutes for questions.